Okay, can you see this slide? And can you hear me? Okay, if okay, let's start the presentation. Good morning, everybody. Welcome to RISC-V Day, Vietnam. Unfortunately, I am in Japan now, but I'm happy to be the opener today. My name is Hideharu Amano of Keio University. Today, I'm going to discuss on RISC-V as a model processor for university education. Well, several years ago, most universities, including Keio, used MIPS R3000 as a model processor for university education. You know, it has a simple instruction set architecture and an elegant 5-stage pipeline microarchitecture. And it has a very rich material, especially textbook. Harris and Harris digital design and computer architecture textbook here is standard textbook for education of digital design. And famous Patterson and Hennessy book and advanced version of Hennessy and Patterson book, all of them used MIPS R3000 as a model processor. And there are rich material for experimental labs, for example, MIPS FPD. But there are some problems. Well, it was somehow obsolete architecture. In the real world, unfortunately, no one used MIPS R3000. And the instruction set architecture is somehow old-fashioned. Of course, there is some ecosystem, but it's rather poor. Okay, so how about ARM? There were some trials to change MIPS to ARM. Some textbooks try to use ARM instead of MIPS. For example, Patterson and Hennessy book and Harris and Harris book published the ARM version, which uses ARM instead of MIPS. Okay, of course, the benefit is very apparent. ARM is the most popularly used computer architecture in the world. So, student has a lot of knowledge for this popularly used architecture. And there is a very rich ecosystem. But there are some problems. Well, ARM actually used complicated microarchitecture and old-fashioned instruction set architecture. It was invented in 1980s, very old architecture. For example, Harris and Harris textbook did the best effort to build MIPS-like ARM 5-stage pipeline, but it is still very messy for students. Ecosystem of ARM is rich, but it is not fully open for education. So now RISC-V is received an attention as an ideal model processor for university education. It was becoming popularly used in the real world, and the ecosystem is rich and fully open to academy. It also provides modern and extendable instruction set architecture, and it takes a simple micro architecture similarly to MIPS R3000. RV32i The base ISA of RISC-V is simple, and there are a lot of extensions. So, and the materials are developing. For example, Patterson's and Hennessy textbook and Hennessy and Patterson textbook published RISC-V edition. Maybe Harris and Harris textbook will follow it. Okay, but there are some problems. First, instruction field of RV32I is slightly complicated. And some instructions of RV32I may stretch the critical path. Well, sorry, Kao-san. My presentation is not for simply admiring RISC-V. I would like to discuss how RV32I is used for education processor like MIPS R3000. But I believe that my presentation and my experience is very practical for university teachers. Okay, so let's review the instruction set architecture of RV32I and MIPS R3000. Major instructions are common, and they take typical RISC-style instruction set, that is, register architecture, fixed size instruction, and well-selected limited number of instructions. For example, addressing mode is only register indirect with an offset. So basically, it is easy to switch from R3000 to RV32I. But of course, there are some differences. This table shows them. First, there are original instructions for each architecture. RV32I provides a branch with comparison, branch greater equal or branch less than. And this 8UIPC is very interesting operation. It can take program counter into the register file. While R3000 provides no instruction, but strangely, NAND instruction is not provided. And it implements jump and jump register for its original instructions. And these load instructions and store instructions are provided for misalignment data. It's messy instruction to implement. And offset, immediate, and branch target are completely different. RV32I uses 12-bit offset or immediate field, and all instruction it is extends the sign bit. But R3000 uses 16-bit, and the sign extension is only for arithmetic instructions. Well, jump and link is somehow different. In RV32I, PC can be saved in any register. So jump and jump register are implemented by using this function. So they are implemented with as suite of instructions. But R3000 uses JAR and JAR-R, jump and link register. And they save program counter into the special register, the last register, register 31. Okay, so comparison is somehow different. RV32I provides two ways. One, is using branch equal or branch not less than. And it also provides set less than, the comparing instruction. But R3000 only provides set less than, comparison instruction. Okay, so the instruction fields are completely different. MIPS R3000 has only three types: R type, I type, and J type. The field of code is 6 bits and it is fixed. It uses 16-bit immediate field here, and the position of register is fixed. But the role of this IP is depending on the instructions. That is, RT can be used both for destination register and source register. On the other hand, there are a lot of types for RV31. The main opcode uses 7 bits for future extension. And this function 3, these 3 bits are used for classifying detailed instructions like that. The location of all registers are fixed, and the role is not changing, unlike R3000. Well, the immediate offset or branch target address is most confusing issue for students. They are divided, and the location of bit is shuffled. For example, branch target is separated to 4 sections. First of all, the top bit, 12 bit is located here. But the 11 bit is located here, and from 10 to 5 bit is located this part. Lastly, 4 bit to 1 bit is located here. Okay, so other instruction has their original formation way to split and shuffling. Well, this location is actually well considered to reduce the hardware. That is, we can only extend the 31 bit for sign extension. And the location of immediate is fixed in order to reduce the multiplexer as possible. For example, from 10 to 5 bits is common. And from 4 to 1 bit is separated into 2 locations, but there are only 2 locations. So actually other bits are located for reducing the multiplexer as possible. Okay, so we evaluated the effect of bit shuffling. The synthesis results, the synthesis is done with very old process, which is now I use in my class. Well, the result shows that the combinatorial area is reduced by 1.3% compared with the case without consideration, without shuffling. But the operational speed is not influenced. Well, so it actually contributes to reduce the hardware amount, but it introduces the problems in education. First of all, hand assemble is almost impossible. It's very confusing. And the Verilog or other HDL description becomes hard to be understood. For example, we use this kind of description for interpreting this shuffle location. Okay, so let's move to the microarchitecture. We show 3 microarchitectures in the lesson. single cycle, multiple cycle, and 5-stage pipeline architecture. Fortunately, the total structures are mostly similar. So if you have materials for R3000, they can be easily changed into RV32I. But I found that the data bus of R3000 becomes slightly complicated. It comes from two facts. The role of RT must be switched. Uh, jump and link and the jump and link register of R3000 need to push special register, register 31, to for storing program counter. So there, it's loses some kind of orthogonality, so introduces a complexity in the implementation. But on the other hand, the compare and branch with size instruction, that is, branch greater equal or branch less than implemented in RV32I, may stretch the critical path. Okay, this diagram shows R3000 single cycle microarchitecture. You can see multiplexer here. It is for switching the role of RT. In RV32I, every instruction is well designed to simplify the data path. So you can see that the total structure is simpler than that of R3000. Okay, so this diagram shows the famous MIPS R3000 5-stage pipeline. It is consistent of instruction fetch, decode, execution, memory access, and write back. So you can see a lot of multiplexers. Well, it's for data forwarding. And there's some hardware is needed to interlock the pipeline. So it introduces some complexity to the pipeline, but I think they are needed to, as an example, for interlock and forwarding, that is to control the pipeline. RV32I 5-stage pipeline it takes the similar 5-stage pipeline, F, D, E, M, and W. And the data path is slightly simpler. But here we need comparator in size. It stretches the critical path by 0.4 nanosecond in our synthesis result. Well, this is the result of synthesis. It evaluated the frequency, clock frequency, and million instructions per second, the performance measure. Sorry, it's confusing for me, the name of processor. Well, we used more modern and practical semiconductor device, United Semiconductor Japan, CMOS 55 nanometer. And the results shows that the speed of RV32I is unfortunately slightly slower than that of R3000. And the performance is also slightly slow. Instead, the power is slightly lower, but it's an obvious result because this evaluation is done with the maximum frequency, which works in the processor. And also the area is larger. It's somehow storage, but it is for enhancing the operational frequency. Well, I thought that the speed of RV32I can be comparable to R3000. So the synthesis result increase the area. Well, so let's compare RV32I and R3000. Clock frequency and million set instruction set per second of R3000 is slightly better. Branch greater equal and branch less than of RV32I really stretch the critical path. And the delayed branch provided of R3000 effectively works. My evaluation is based on the students' design of program. They used delayed branch and they use branch delayed slot in delayed branch. So the performance is slightly improved. But both architecture can work at 60, 150 megahertz clock. Often USJC 55 nanometer process is used. So I think it's not too bad. But in this evaluation, memory delay is not included. Uh, okay, and the area and the power are mostly similar in both architectures. Okay, this is the summary of my presentation. RV32I is a very good architecture as R3000 as a model process for university education. The instruction set architecture and microarchitectures are mostly similar. So there is almost no barrier to change the model architecture from R3000 to RV32I. But the complicated bit field is somehow confusing for students. Actually, it slightly reduces the hardware, but the effect is not so large. And the performance of R3000 is slightly better than RV30I. Okay, so these two issues contribute to it. But it's somehow obvious result because R3000 is optimized for 32-bit RISC architecture, while RV32I is designed as a base of many extensions. So it's a reason why RV32I does not use delayed branch. And the complicated field is to keep the space of extension. I think that it's very important to make students understand these issues. So maybe RISC-V is very useful in the advanced course of computer architecture because the extended instruction will be used in various fields of computer architecture, including the multiprocessor and vector processor and something like that. Okay, so my conclusion is that RV333-I has some faults as a model processor, but it will be broadly used as for university education. Thank you very much.
Thank you, Mr. Professor Amano. And it's start Q&A session. Okay.
Okay, any question is welcome.
Yes, and
yeah, unfortunately, this presentation is for university teachers. So if you have no experience about the teaching, so this is not so interesting. I'm sorry.
okay. So everyone, please QA this presentation. So I announce again how to ask, and so please wait a minute. You can ask this presentation from Twitter. So this presentation title is this session. So you can apply this Twitter. And Professor Amano, I get one question from the audience.
Oh, great.
So the question message is, what is the main barrier to use RISC-V in university experiments lab?
Oh yeah, thank you very much. Yeah, it's actually now well, there is no good no good materials for example, the design in FPGA. Of course, there are a lot of design examples in RISC-V, and it's easy to be implemented on FPGA. But for working a practical problem, we need some material for FPGA. Maybe, well, actually the MIPS provider, MIPS FPGA. So something like the similar product will be needed for RISC-V education. Thank you.
書き込んでる？ チャットに1個質問来てますね。
Okay. Thank you. And one more question from chat this conference. And wait a minute. すいません。
Twitter に来てる。
Twitter に来てる。これか。Okay. Second
QA
from Mr. Tan Tran. And the design was done by students, so there is a difference in frequency. It is done by the experienced engineer. Then it is no difference in frequency.
Oh, you did it. It's great. Yeah, actually, the frequency comes from the this part. Sorry. The frequency degradation of RISCs RV32 comes from the branch compound branch instruction. MIPS R3000 only provides the equal, not equal instruction. But unfortunately, RV32I provides a branch greater, equal, and branch less than. So in order to solve this problem, we may move these instructions to this stage. Maybe the best solution I was suggested is to implement equal, not equal instruction in the decode stage, and these comparison inside instructions is executed in the next stage. Of course, the delay for branch will be increased, but if the frequency or of using these instructions is not so many, not so large, it's a reasonable solution. So if you do so, the clock frequency of RV32I is better than that of R3000 because the total structure is rather simpler.
Okay, thank you. And
There is
one more question, okay?
Uh-huh.
I think
待ってください。
笠原さんから来てるんじゃん。はい。お願いします。ちょっと待って。あれ。あ、来てます？見えてます？あ、見えてないです。
I'm sorry, I can't see it.
あれですか？いや、今ね、ちょっとツイッター探してんの。はい。
Oh, sorry, I don't see the check the Twitter. I forget it.
Okay.
Yeah,
We
are on chat.
私も送ったって言ってる。
I can answer it later.
Okay.
Okay.
Yeah, we still have 3 minutes. Sorry.
That's no problem. Yeah, I will answer the question anytime. So please give me.
Sorry, third question. And this is from chat. Miss Gmail, Gmail address get. And this question is, we should divide the decoder phase into 2 phases and maybe add a branch predictor.
Yeah, that's right. It's a good solution. Yeah, maybe we should. Yeah, very good solution. Yeah, branch instructions into 2 categories under a user simple branch prediction. Yeah, it's very good exercise for students.
Okay, thank you. So the last question. Okay.
Okay.
What do you do with things that are not defined in RISC-V, such as prediction and condition move? And I think it's an important architecture. Yes, this ends.
So it's like predication, condition move.
Well, it's a possible extension, but I feel that it's too high level for beginners. Yeah, actually, I suppose that this kind of RV32I is used for the beginners. And of course, RISC-V provides a lot of extensions, so they can be used for advanced course of computer architecture. Thank you.
Thank you. And this session is ended. Thank you, Professor Amano. Thank you for very much. Your presentation.
Okay.
Yes,
so I will stop my sharing. Okay.
Okay.
And quick.
Thank you very much.